All right, today we're going to demystify a really core concept from one of the most powerful operating systems on the planet, Z/OS. We're diving into the address space, which is basically the secret sauce to how it runs thousands of programs at once without a single one taking down the whole system.
So let's just start with a really fundamental question. You think about any computer, but especially a mainframe. You've got countless things happening all at the same time. How in the world does the system stop one rogue application from just causing a total catastrophe? Well, the answer is actually pretty elegant.
And that answer is the address space. In ZOS, every single program, every user who logs on gets their very own unique address space. It's this continuous block of virtual memory, a completely private universe where a program does its thing, runs its code, stores its data, all totally walled off from everything else. Yeah, the easiest way to really picture this is to think of it like a secure digital bubble. Inside that bubble, the program has everything it needs to survive. It can't see out, and, way more importantly, nothing from the outside can just barge in and mess with what's going on inside. It's its own private workroom. Total focus, zero interference. Now, I get it. This might sound a little abstract, especially if you're kind of new to the whole mainframe world. So let's build a bridge from this idea to some concepts you might already be familiar with from other systems.
If you spend any time at all in the Linux or Unix world, this is where you're going to have that big aha moment. A ZOS address space is really similar to a Unix process, and its unique identifier, the ASID, is pretty much the same thing as a process ID or PID. And the little tasks running inside that space, the TCBs, well, those are just like threads. See? This comparison gives us a fantastic frame of reference.
So, okay, we know what an address space is now. But what about the why? Why is this design so powerful? What exactly makes this bubble concept a genuine superpower for keeping a system stable and secure?
First off, let's just talk about sheer scale. A single ZOS system isn't just running, a handful of programs. It is orchestrating thousands of these address spaces all at the same time. One for every job, every single user, every critical system function. The volume is just mind-boggling.
And that massive scale is only possible because of that strict isolation we talked about. If one program goes haywire, the problem is trapped inside its bubble. It can't spread, it can't cause this horrible domino effect across the system. And this doesn't just protect other programs and keep data secure. It makes the entire system incredibly reliable. Plus, when something does go wrong, figuring it out and recovering is so much easier because you know exactly where the problem is contained. This really gets to the heart of the security philosophy here. And hey, don't just take my word for it. The official documentation says it best. This isolation provides much of the operating system's security. This isn't just some nice feature for stability. It is a foundational pillar of the entire security model. By keeping everything separate by default, security is literally built in from the ground up. Okay, so we've established that everything is locked down tight in its own private bubble for security. But this brings up a new and really important question. What happens when these programs actually need to work together? Right? I mean, in any complex system, applications don't just exist in a vacuum. They have to share data, they have to collaborate. So if every single program is in its own little protective fortress, how do they communicate without completely wrecking the very security that makes the system so strong in the first place? Well, the answer is that ZOS doesn't leave something this important to chance. It provides very specific, very secure, and very controlled ways for what's called inter-address space communication. It's like having a secure, guarded checkpoint between those private workrooms. You don't just wander in. And this communication really happens in two main ways. The first is an asynchronous method, which uses something called a service request block, or SRB. The second method is synchronous, and it uses what's called cross-memory services. Let's break down what that actually means. So, using an SRB, it's kind of like sending a secure message or a work order over to another address space, and then just getting back to your own business. It's asynchronous. You just fire it off and you trust the system to handle the rest. Cross-memory services, though? Totally different. That's synchronous. It's like making a direct phone call. You dial, you establish a connection, you do what you need to do, and you wait for the result before you hang up and move on with your day. But here is the most critical difference, and it all comes down to authority. In a system like Unix, you can often use shared memory without needing any special permissions. But ZOS is way, way stricter. To use the super powerful direct access of cross-memory services, a program needs special APF authority. This is a huge security feature. It makes sure that only programs that are explicitly trusted can ever reach into another program's private space.
So let's bring all of this together. Why does this design, which actually goes back decades, still matter so much today? Well, it all comes down to this absolutely brilliant balancing act.
What we've really been looking at is a masterclass in design philosophy. The ZOS address space perfectly balances two needs that are often fighting each other. On one hand, you have this profound, hardware-enforced isolation that gives you unbelievable security and stability. And on the other hand, you have these carefully controlled, authority-checked channels for communication that let complex apps work together safely. It really is the best of both worlds.
And this kind of leaves us with one final thought to chew on. In our modern world of interconnected systems, constant cybersecurity threats, and all kinds of vulnerabilities, is this classic mainframe idea of strict, enforced isolation actually more relevant today than it has ever been? It's definitely something to think about. Thanks for tuning in.